Hello and welcome to today's IWCS webinar. My name is Connie and I'll be the Cisco producer for today's event. Now I am pleased to turn the webinar over to Ed Fitton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we welcome Steve Zimmel, Principal Product Development Engineer for CommScope in Shakopee, Minnesota, USA, who will be presenting his paper on a new factory Splice-On fiber optic connector with high performance and reliability by machine automation. Steve Zimmel received a BA in Physics from Gustavus Adolphus College in 1994, a BS in Mechanical Engineering from the University of Minnesota in 1996, and an MBA from the University of Minnesota in 2002. Steve has been with CommScope since 1995. He is currently Principal Product Development Engineer at CommScope, focusing on fiber connectors and other interconnecting devices. Steve holds numerous patents and also represents CommScope on TIA TR-42. Steve, we welcome you to present at today's IWCS webinar series event.
Hi, thank you. So what I want to present is a new SC and LC connector design whose design enables automation. So we want to present the design, what it's all about, and then demonstrate its performance and reliability. The new design uses it's a pre-terminated stub that's built by automation, and that fiber stub is later fusion-spliced to the optical cable. This describes the current way that connectors are usually done. You know, right now, LC and SC connectors, they're pretty much the industry standard. The SC is the standard in telecom central offices and outside plant networks, whereas the LC is more or less the standard in any sort of data center or supercenter environment. And as the listeners are probably aware, you know, in all of this time, these connectors are factory terminated with processes that have largely been unchanged, and they're mostly done with manual labor. The basic process is propping the cable by stripping it, potting the fiber into the connector with epoxy, and then a polishing operation. And these processes have basically been unchanged over the decades, and they're pretty manually intensive. So in the past, you know, attempting to automate the assembly of these connectors has been problematic, mainly because of the long length of cable that we have to attach them to. It's especially problematic when there's high fiber count cables or long length of cable behind it. As the picture shows there, this is it's a 288 fiber cable, and to terminate this with automation is hard because you can't move that spool of cable from one station on automation to the next until all 288 fibers have completed that step. And so there's a lot of challenges in material handling and material flow when you try to automate the traditional process. We overcame this by designing a connector that has a pre-terminated fiber stub. That's shown in the lower right-hand picture. So the way that this works is that the ferrule is potted with a very short length of fiber. And so, you know, maybe 25 millimeters long. And so because of that, there's no long cable behind of it that creates material handling issues in automation. And so what the picture shows there is the automation that we did to make these stubs. And basically, in goes at the front end into a bowl feeder the ferrules, and out at the other end comes a ferrule-stub assembly that's shown on the right picture. And this ferrule-stub has been potted, and polished, and the epoxy has been cured, and it's been fully tested for end face geometry and for workmanship, things like scratches and pits. And the reason this works is because there's a very short length of fiber behind it, so the cable handling burden is eliminated. And so that makes it a lot easier to automate. And the other thing it does is that the critical steps in a connector, such as the epoxy cure and the end-face polishing, they have a significantly improved quality because the operator variability has been eliminated. So the next step in this connector design is to terminate it. And this is where, the benefits really come in. And so as opposed to the old method where you pot, polish, and test on your termination line, that's all been replaced by a splice and overmold operation. And this splice and overmold operation is really, it's a lot more straightforward than the potting, polishing, and testing. It's a lot cleaner, and it involves a lot less operator dependency and a lot less operators. And so the picture here shows the new termination line. And this can be staffed by 5 people, as opposed to a traditional termination line, which has at least twice as many people. And it can produce the same number of parts per hour. But the basic process is step 1 is that the fiber stub, the fiber behind the ferrule is prepped, so it's stripped, cleaned, and cleaved. The second step is to fusion-splice it to the optical cable. The third step is to overmold it, and in this design it uses a UV curable adhesive. And then after the splicing, the connector is assembled over it, or the connector components are assembled over the ferrule. So the design is a bit different, too, to accommodate this process. And the picture below, or the picture in the lower left, shows a cross-section of what this spliced ferrule-stub assembly looks like. And the thing that's unique about this is that the splice is only 3 to 5 millimeters behind the ferrule. And that's different from other Splice-On connectors that exist out in the industry, in that it's really, in that close to the ferrule, it can be inside the permanently attached ferrule flange, which is formed in this design by an epoxy overmolding operation. And so what this does is it allows the length to be the same as a normal connector, which helps comply with the length requirements of GR 326 and the IEC. Also, by keeping the length the same as a standard connector, it helps compliance to the IEC and GR 326 side pole mechanical performance. So, this new design, it differs from traditional factory terminated connectors in that there's a splice very close to the end face. And that splice in close proximity to the end face can affect the optical signal and can also affect the reliability characteristics. Because there's a splice there, and that adds loss to the connector. The presence of a splice close to the end face can induce modal interference. And the epoxy overmolding, or the overmolded epoxy that's on the length of the bare optical fiber, can increase the stress in the fiber in outside plant conditions. But the key here is that the automation of the ferrule-stub and the tightly controlled splice inputs done in a factory splice environment enables these splice effects to be largely minimized. So the first, so for attenuation, the automation of the stub, of the little ferrule-stub assembly, allows low loss in 4 ways. The first is that we can tune the ferrule for free, basically. And ferrule tuning is where you rotate the ferrule such that the fiber core eccentricity is located with the connector key. And it's a pretty common operation, especially in grade B products for IEC and EMEA customers. But tuning on a traditional process is a labor-intensive process, and it's pretty expensive and burdensome. But because it's done on the automated system, it's basically done for free. The second thing is that we can use the custom optical fiber in the stub. Because the stub is so short, that means that relatively little fiber is used. And that means it's economical for custom fiber preforms to be made and drawn. And these custom preforms can be drawn with extremely tight cladding IDs and extremely low core cladding concentricities. And so and in this process, that's what we do. We contract with a fiber manufacturer to make very tightly toleranced fiber to be able to use in the fiber stub. And so all of that allows for a reduction in the fiber core at the ferrule end face, or the ferrule core offset at the fiber end face. The third thing that the automation does is that, on an APC connector, because you do the APC grind on the ferrule, and because the ferrule hole isn't straight, it's at a slight angle, as you grind it, the fiber core position can change as the ferrule ID drifts from the center. But again, because it's automated, the polishing is completely automated, we can tightly control how much ferrule material is removed and minimize that effect. And then the last thing that helps keep attenuation low is that we're able to achieve really low splice losses in the factory because it's being spliced under factory conditions. And so the things that really affect splice loss, like the cleave angle and other parameters, can be much more easily controlled than in the field because it's pretty straightforward to implement high-quality cleaving methods in a factory. This slide shows the attenuation we can get from this product. And all of those things that I just mentioned, how to reduce loss, they all add up. And the data shown here is from the Verizon TPR 9409 FOC test program that this product went through. And the histogram of attenuation shows that it's quite low. But what it really does compared to normal connectors, normal type connectors, is that normal connectors insertion loss distribution has a long tail. The average is quite low, but they tend to have a long tail that extends out beyond 1 dB. But because we're able to control all of the inputs so tightly, we basically eliminate the tail of the attenuation distribution. It can have very tight distributions, all less than 0.3 dB, interrelated product to product, with an average of less than 0.1 dB. So to address modal interference is what happens when there's two events in a single mode optical fiber that are spaced closely together. And so when this happens, when there's a fiber, like a splice close to the fiber interface, that can excite the higher order modes. And if the second interface is close to the first one, the power that was coupled into the higher order modes can be recoupled from the primary modes, causing wavelength dependent loss. And the mechanisms are shown below. But basically what happens is that as you measure attenuation across the telecom wavelength of 1260 to 1625 nanometers, you see it can create a variation in attenuation with wavelengths. But with this design, we're able to minimize modal interference with two methods. The first is that the reduced splice and connector loss that we previously mentioned is a big one. And that's because loss variation with wavelength is reduced by minimizing the power available to be recoupled back into the primary modes. And so by having very low loss splices and low loss end faces, the power that's there to be recoupled is minimized. And so the two charts below kind of quantify how this works in this design. And we produced a couple splices intentionally with high loss just to demonstrate the effect. But you can see there's pretty decent correlation between the average attenuation, which is on the x-axis, and the peak-to-peak attenuation, which is on the y-axis. So that peak-to-peak, that's on the y-axis, is the maximum minus the minimum for any connector across the given wavelength band. And then the average attenuation is the average across that band. So you can see, as you can see from the chart on the left, the peak-to-peak variation is smaller as the average attenuation gets smaller. The other thing that we do to help minimize modal interference is the custom preformed fiber is also custom made to have a low cutoff wavelengths, much lower than the requirements of the ITU specs. And if the connector is operating at a wavelength that's well above the cutoff wavelength, and that tends to reduce the effect at the lower wavelengths. The next topic about this is reliability of the connector. as you can see from the picture on the right, there's about 6 millimeters of bare fiber, which is encapsulated in epoxy. And this is like the fiber in which the cladding has been removed, so it's the bare glass. And so this is, different from a standard connector in that there's quite a bit more bare fiber in epoxy. And the thing about epoxy is that they exhibit hygroscopic swelling in humid environments, which can increase the strain on the fiber. And so that coupled with the fact that splicing can form fiber defects on the cladding that serve as cracked nucleation sites, these two things needed to be addressed in this design. And the method to ensure the reliability is that the splicing operation is 100% proof tested prior to overmolding to screen for defects. And then the other thing is that the epoxy that is used to overmold the splice is very low CTEs, to coefficient of thermal expansion, to counteract the hygroscopic swelling effects. And the epoxy that's used, it's a 70% glass-filled UV curable epoxy that has a heat cure component also. And so we were able to measure the stress on the overmolded fiber. We were able to measure the stress by, instead of potting a normal fiber in there, we potted a fiber braid grating into the overmold and measured the stress as a function of environment. And we were able to make reliability predictions. And that's what this next slide shows. The chart on the upper right shows the wireable slope of the splice strength. Basically, we took a large number of splices and pulled them to failure. And by doing that, you're able to plot the wireable slope of it, and that can be used in the reliability calculations. These reliability calculations are well developed from the fiber industry. The equation below that's shown there is the equation that was used to calculate the p-value. And so we were able to measure. The other thing that we need to know then is the stress. And the chart on the lower right-hand shows the stress of the fiber braid grating that was potted inside of the overmold as a function of all of the GR326 environments. And so the environments that this went through, then that this specific sample went through, was 7 days of 85 degrees C thermal age, followed by 7 days of thermal cycling from -40 to +70, followed by a week of humidity age at 75 degrees C and 95% humidity, followed by a humidity condensation cycle, and finally followed by another thermal cycle. And throughout that entire time, the maximum stress that was measured was 0.12 gigapascals. And so then by using that maximum lifetime stress, we were able to calculate the failure probability. And that's shown in the table on the lower left to 15 and 30 years. And the failure probability calculations are very, very low, given the stresses and the splice strength that this process can produce. So we were able to further demonstrate reliability by putting this through a third-party GR326 test program. And these connections went through the full Verizon TPR 9409 FOC testing, which is basically GR326 testing performed by an independent third party. And throughout the entire service life testing, which is a rigorous 5-week test of extreme environments, there were no failures, and the insertion loss was very stable across all tests, as shown in the chart below. The chart below shows the attenuation variation at 1310 nanometers during the service life testing, and the maximum change on any connector was less than 0.1 dB. The connector also went through the 2,000-hour humidity age, thermal age, and thermal cycle tests of GR326 without failure. So to summarize, the automated Splice-On factory terminated connectors, we were able to demonstrate they had at least equal and sometimes better performance than a standard factory connectors through really three things. One is the attenuation. We're able to reduce that by using the advantages of automation. The second thing is that the modal noise can be minimized by using low-loss splices and fiber with low cutoff wavelengths. And the reliability can be demonstrated by proof testing the splices 100% in production and by proper epoxy selection. That wraps up the presentation.
Great. Okay, super. Thank you very much, Steve. And at this point, I will take as many questions from the attendees as time permits, starting with this first one. Is the manual termination usually done by the cable manufacturers or by third-party harnessing assembly plants?
Usually by third-party plants. Usually the cable manufacturing is done by one company, and then the factory termination is done by a different company, although a lot of times the same company will make the fiber and cable. For example, CommScope, we make fiber and cable, and we do connector cable assemblies. So do other large companies like Corning and OFS. But even in those situations, they'll be done in separate factories at separate times.
Okay. Next question. Considering the difficulties in precision required for fiber optic connectorization, are there major conformance or quality issues in the market due to manual variability, especially from low-cost internet sources?
The manual process can create reliability issues. There's two things it can do. One is because the process is manual, it's not difficult to damage the fiber during the handling of it. And so that creates a potential reliability risk in the field over time of fiber fracture if the operator isn't well trained. The other thing, and this isn't so much a customer concern, but the manufacturer's concern, is that the manual process can create a lot of rework if the important parameters aren't in spec when they're inspected. For example, end-face geometry, which was kind of the measurement of how well the ferrule was polished. The yield on that is not always great, and so that creates a lot of rework in the factory termination plant. And by automating it, you basically eliminate that rework.
Okay. Thank you. Next question. What is the average splice attenuation loss for standard manual connectorization versus the 0.025 dB loss in the automated process?
Well, splicing in the field is, that will probably average maybe anywhere 0.05 to 0.15 dB. But, when you're doing this in the field, whether you're splicing on a connector or whether you're splicing cables together, it's not really part of the connector spec. And so I think, there's more tolerance for a slightly higher splice loss in those situations than in a factory terminated connector, because in a factory terminated connector, it's expected to have loss that's quite low, whether there's a splice there or not.
Okay, thank you. Next question. About the overmold. Where is it done? In the factory? So this makes a connector not a field installable one. Am I correct?
The product that we developed is specifically for factory termination, and so it's done in the factory. The epoxy overmolding is.
Okay. Next question. Regarding data for SC/APC, is SC/APC also tuned as was discussed for LCs in the slides?
Yeah, we in this process we tune UPC and APC.
Okay. Does CommScope offer this connector and overmold equipment to other parties?
Right now we don't. But I think in the future that might change.
Okay. Next question. What technique or tool is needed to strip the coated fiber?
The methods that we developed are proprietary because that stripping method has if it's done incorrectly, it can have an effect on the fiber reliability. But generally speaking, fiber stripping can be done by any number of methods, and there's a lot of equipment that's available to do it. There's manual methods, there's semi-automated methods, there's heat methods, and there's also, those are the traditional methods that are done.
Okay. Next question. How is it made sure that the ferrule interface is kept clean after coming out of automation? There seems to be a sequence of processes that have to be done with the ferrule fiber stub assembly after it has been tested in the automation machine.
In the automation machine, after it's been potted, polished, and tested, it's cleaned through an automated ultrasonic cleaning system, and then a dust cap is placed on the end face and sealed, and it's sealed for distribution to the termination plants.
Okay. Are there specific industry standards and third-party verification of performance for SC and LC connectors? Are there independent listings that a user should specify?
It depends so in general, yes, there are, and it depends largely on the market you're in. For North America, for the telecom market, it's GR326. For North America data centers, it's TIA 568. And then for any place outside of North America, the rest of the world, those are driven by the IEC. And so for data centers in the global markets, it would be the IEC Category C performance requirements. And for telecom markets, for the rest of the world, it would be the IEC Category U requirements. And getting certified, whether it's through some third party or not, that's really, there's no rule out there that says they have to be, but individual customers or service providers may require that. For example, large telecom operators like Verizon in the United States or Telefonica in Europe and South America, they would require your connectors to be verified to the applicable standards by some third party. And basically what that means is that the third party would have to perform the tests and then write the report.
Okay. I am showing no further questions. So thank you, Steve, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Steve after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be held on Friday, October 20th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 65 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 8th through Wednesday, October 11th, 2017 at the Gaylord Palms in Orlando, Florida, USA. In addition, the second annual regional UL and IWCS China 2018 Cable and Connectivity Symposium will take place on Monday, March 19th through Thursday, March 22nd, 2018 at the Pudong International Convention Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.